This is the first of a couple of videos I'm going to make about regularization. So regularization has to do with the bias variance trade-off. Regularization is a way of reducing the variance of a model. And often when you use regularization to reduce the variance, the bias only goes up by a little bit. And so the total error can be better. Since this is our first video on this topic, um, we can think about just the regular error function that we normally work with. We usually call that En. Is that color good? It's a different color. Let's just use black. So our in-sample error is a function of the weight vector W that we find. So what we normally do is we let the best W, you want to call it like W star or something, this is equal to the argmin of En W bar. So it's the weight vector that produces the lowest end sample error. So that's the most obvious thing to do. So there's variations on that, and our textbook Learning from Data calls this the augmented error. And so it's the ordinary end sample error, and then it's plus, let me just call this omega of W bar. And so this omega function can take different forms, but what this is a complexity penalty. So the idea here is something like Occam's razor. If you've ever heard of Occam's razor, it's the adage from the scholastic philosopher from like what, the 1100s. I don't know. Check Wikipedia and embarrass me on that. But Occam's razor is the principle that says that when you're trying to discover propose a model for something, you want to find the simplest model that explains the data. So so this form, the augmented error, kind of takes that into account. So you want to find something that balances, that minimizes the sum of the in-sample error. So this is how well W fits the data, and this is how simple W is. So the form that this usually takes is something like the sum of the squares of the entries in W. So W is length d plus 1 for us. And so this is the way that the book would do it. So what is this? This is sort of like the it's like the length of W squared. And in we want to be a little bit more sophisticated than this. Usually there's also a scaling factor, lambda, here. So lambda is an example of something called a hyperparameter, which is going to depend on your algorithm and your data, and you're going to have to do some kind of search when you're doing your model selection process to find the lambda that works best for whatever problem that you're trying to solve. But let's just kind of try to understand the intuition behind this with like a very, very simple regression problem with just one-dimensional data. So here's a regression problem with one-dimensional data. Maybe some points look like this. And we're trying to fit these points with a line. And so a line could be like W0 plus W1 times X1, where this is the X1 axis, which is the only data axis here. And then this is Y. So the line that fits this best might be something maybe like this. Whoa. So this will be kind of a very steep line. So look, it has a very low intercept. So W0 is way down here. And also it's steep, so W1 is also big. So for this solution, W0 squared plus W1 squared is going to be large. How should we say that? Much bigger than 0. Okay, so this, in this understanding of what complexity means, this would be a relatively complex solution. What would a simpler solution be? A simpler solution might be something like this. Um, so let me do even better than that. So actually, we can totally minimize the magnitude of W0 just by picking something that goes through the origin, and then we'll give it kind of a modest slope. So now the slope is lower and the intercept is 0. So now for this other line, the orange line, W0 squared plus W1 squared is going to be much less than with the other color. So in other words, not too different from 0. So which one of these will generalize better? Um, so just as a matter of experience, it often happens that the simpler solution really does work best. And we can give some visuals on that too. There's this kind of technical point about whether you should include W0 in this regularization process. So our book, Learning from Data, does apply the regularization penalty to the intercept W0. But our other reference book, which is Hands-on Machine Learning with sklearn, um, that says that you should not penalize the bias weight. And that kind of makes sense in a certain way. If you're talking about, you want to find like the simplest shape, right? You want to find the simplest shape that explains the data, then you don't necessarily care what its intercept is. So if that's your philosophy, then you don't want to regularize W0. So when we do the derivations, eventually we'll do it both ways. But if you were following the presentation in hands-on machine learning with sklearn and TensorFlow, then you would start this counter at 1 instead of 0, even though W0 is there. Okay, so let me stop this or pause this. I'm going to stop sharing my screen if I can get the cursor to go where I want it to go. And I'll pick this up again in another video that I'll record soon.